Calculus students, hello. In our last lesson, we saw a portion of the fundamental theorem of calculus where you use antiderivatives to help evaluate definite integrals. Now, because antiderivatives are so useful in calculating the value of a definite integral, we use the same notation, but no limits of integration. In other words, you'll see an integral sign without a number below and above it, some sort of function that we call the integrand, and the differential to help identify the independent variable. And this notation represents the general antiderivative of the integrand. This is called an indefinite integral, whereas a definite integral had x values above and below the integral sign and represented the limit as n goes to infinity of some Riemann sum. Use your knowledge of derivatives to find the result of each indefinite integral below. Generalize your findings. So the integral sign in the dx is now a notation to suggest we want to find the general antiderivative of this function here called the integrand. So if this is some function f of x, our goal is to find some capital F function where capital F prime gives me little f. Capital F is called the antiderivative of little f. I know that when I differentiate x to a power, using the power rule, the power will drop by 1. So in my integrand, I see that there's a 1 power on this x. So I know my antiderivative should have an x squared. But the question now becomes, what coefficient should I put here so that when I do the power rule, I get just x? Well, currently if I differentiate, I get 2x. So I'm going to put a 1/2 in front of this so that when I differentiate, the 2 and the 1/2 will cancel, leaving a 1. The power 2 will drop to 1, and so my derivative will just be x. Now, of course, to this function, we can add any constant, such as 3, because when I differentiate this function, the 3 will go away to 0. So we could really put any constant here, and we have what's called a family of antiderivatives. This represents infinitely many possibilities because c can be any real number. It's called the constant of integration and can be any real number. So this entire expression is our capital F, and there are infinitely many. Okay, the next example. If my power after differentiation is 2, then I know prior to differentiation, I needed it to be x cubed. So once again, what coefficient should I put here so that when I do the power rule, 3 times that number needs to be 1. So I need that number to be 1/3. And then, of course, add any constant. Next example, if the power here is 3, then prior to differentiation, I needed a 4 power, and I need to put a number here so that 4 times that number will be 1. That will be 1/4. And then, of course, plus c. So you can see a pattern here, a sort of reverse power rule, or we can call a power rule for anti-differentiation. That if you have x to the n and you want to find the antiderivative of this, then we need to increase that power by 1. And then in front, I need to have a coefficient of 1 over n plus 1. Of course, you could also write this by multiplying this x up to this numerator and express our formula this way, and then plus c. This will become a rule that you'll use so much that you'll effectively memorize it. Of course, the rule only makes sense if we have a non-zero denominator. This rule would clearly fall apart if n was -1, because then the formula would have us divide by 0, which is not possible. This suggests we need a different formula for the case where n is -1. If you change this n to -1, then you have x to the -1, which is just 1 over x, which will be our next example right here. So if n is -1, we will get a different result. Now you may recall a function whose derivative is 1 over x. That function is the natural log of x that we learned earlier in the course. The derivative of natural log of x is 1 over x. And then, of course, plus c. We do have one caveat we ought to mention here. Since we're starting with the function 1 over x, we want to be mindful of its domain. The only x value not allowed in 1 over x is 0. X can be negative, it can be positive. However, in the natural log of x, this x must be positive because you can only do natural log of a positive argument. So we have a change in domain, which I would like to avoid. Now the way around this issue is to put the argument of this natural log in absolute value bars. Now, the only restriction on x is that x can't be 0, and then these two domains now match. Furthermore, the derivative of natural log of absolute value of x is also 1 over x. Next example. The best way to approach this one is to rewrite the integral as x to the -2 dx. And then from here, we get to use this formula because this formula works for every n except for -1. So the antiderivative, add 1 to the power, -2 plus 1 goes to -1, and divide by that new power, and then plus c. Then of course another way to write this though would be -1 over x plus c. In this next case, rewrite as x to the -3 and use the power rule for anti-differentiation. Add 1 to -3, it becomes -2, and divide by that new power, and then plus c. And of course, we can rewrite this so we get a -1 over 2x squared, and then plus c. In the case of radicals, just reinterpret as powers and use the power rule for anti-differentiation. Square root of x is just x to the 1/2. So the antiderivative of this function will will be add 1 to that power, 1/2 plus 1 is 3/2, and then divide by that new power, and then plus c. Now dividing by 3/2 is the same thing as multiplying by 2/3, and x to the 3/2 is the square root of x cubed. So here's an alternate way to write our answer in the end. Next example, the cube root of x squared is the same thing as x to the 2/3 power. It now used the reverse power rule, so add 1 to 2/3, that becomes 5/3, and then divide by 5/3. So divide by 5/3 is multiplying by 3/5, and x to the 5/3 is the cube root of x to the 5th. So here's an alternate way to write your answer. Now 1 over the 5th root of x can be rewritten as 1 over x to the 1/5, which is the same thing as x to the negative 1/5. And we still use the power rule for anti-differentiation. So add 1 to negative 1/5, so negative 1/5 plus 5/5 is 4/5, and then divide by that new power, and then add c. 1 over 4/5 is 5/4, and x to the 4/5 is the 5th root of x to the 4th. So two rules emerge on this page that are important when n is not -1, and then when n is -1. Note that computing an indefinite integral is also known as anti-differentiation. I've been using that word. The term integration we should now use more generally because it can now refer to computing either indefinite or definite integrals. So everything I've done on this page you can call both integration and anti-differentiation. But integration can also be used for when you're computing a definite integral. Okay, let's go to the next page. Use your knowledge of derivatives to find the result of each indefinite integral below. Generalize your findings. In this first case, our integrand is just 3, so we need a function whose derivative is 3, and the independent variable needs to be x, so that function will be 3x. The derivative of 3x with respect to x is 3. And then, of course, add our family of constants. In this next case, 2/3 is just a constant still, so the antiderivative with respect to x is 2/3 times x, and then plus c. In a case where all you see is an integral sign and a differential, keep in mind that the operation between an integrand and differential is multiplication. So when you see a differential that apparently has no integrand next to it, there is an implied 1 there, multiplying to that dx. So the integral of just dx, we are looking for a function that when you differentiate it with respect to x, you get just 1. Well, that function will just be x, and then, of course, plus c. So here's a general rule. If you have any constant here, the antiderivative with respect to x will be that constant times x plus c. Okay, next example. The derivative of e to the x is also just e to the x. So the integral or antiderivative of e to the x is e to the x, and then, of course, plus c. Now, recall that when you find a derivative with respect to x of e to the u, where u is some other function, that the result is u prime e to the u. So specifically, when you differentiate e to the 2x, we would get the derivative of 2x, which is 2, and then e to the 2x. So when we're integrating e to the 2x dx, I want a function whose derivative will just be e to the 2x. Well, if I put e to the 2x here and check it, the derivative of e to the 2x is 2e to the 2x. But there is no 2 coefficient here. So I need to put a coefficient here so that when I do the chain rule, the multiplication by 2 will cancel and leave a 1 instead, suggesting I need to put a 1/2 right here. Now when I differentiate this function, the 1/2 would stay because this is a constant times a function. E to the 2x would repeat, and then we would multiply by 2, which would cancel with the 1/2, and the derivative therefore would just be e to the 2x, matching this integrand, and then plus c. Next example, best to rewrite this as e to the negative 3x dx, and then use the same principle. The answer will be e to the negative 3x with some coefficient here, so that when I differentiate, the derivative of e to the negative 3x will be itself times a negative 3. So I need a coefficient such that that coefficient times negative 3 will become 1. Well, that coefficient, therefore, would be negative 1/3, and then plus c. In general, if you have e to the kx, where k is a constant, the antiderivative will be itself e to the kx times the reciprocal of that k. This is not to be confused with the fact that when you differentiate e to the kx with respect to x, you get k e to the kx. Next example, recall that the derivative of b to the x is itself times the natural log of b. And specifically in the case of 2, the derivative of 2 to the x is 2 to the x times the natural log of 2. The derivative of this exponential produces itself, but times a constant. So the integral of 2 to the x will be itself, but we'll need to divide by that constant. And we'll need a 1 over natural log of 2 as a coefficient. Because this is just a constant, differentiate 2 to the x is itself times natural log of 2. So this coefficient would become a 1, and we would just have 2 to the x again. Now you can also write this one with the 2 to the x in the numerator. 2 to the x divided by natural log 2, and then plus c, of course. Following the same pattern, the antiderivative of 5 to the x will be itself, but instead of multiplying by natural log of 5, which is what we would do for differentiation, we would divide by natural log of 5 and then plus c. Next example, we have a complication. We have an exponent that's not just x any longer. So recall that the derivative with respect to x of b to the u, there are 3 components to this derivative: b to the u, natural log of b, and u prime. So specifically, when your u has the form kx, then this u will also be kx, and the derivative of kx is just k. So when you differentiate b to the kx, you get itself, and then times 2 constants. So the antiderivative will have to divide by both of those constants instead. So the antiderivative of 3 to the 4x will be itself, and we have to divide by 2 things: the natural log of the base, and then the derivative of 4x, which is 4. Be careful you don't multiply the 4 and the 3 and say 12, so it's better to write this as 4 times natural log 3 plus c. So in general, the antiderivative of b to the kx will be itself, divide by k natural log of b plus c. So on this page, 3 general formulas emerged that we can now use moving forward. Next page. Use your knowledge of derivatives to find the result of each indefinite integral below. So we're investigating some trig, inverse trig, and hyperbolic trig. The antiderivative of sine of x. Well, we know that the derivative of sine and cosine go back and forth, producing negatives occasionally. So I suspect that an antiderivative of sine will be cosine of x and then plus c. But let's test it. The derivative of cosine of x is negative sine of x, and there's no negative on this sine of x. So we can adapt and put a negative here, so that when I differentiate negative cosine of x, I get now just positive sine of x. Obviously, this opens the door for potential confusion because the derivative of sine of x is positive cosine of x. And now we need to remember that when I anti-differentiate sine of x, I get negative cosine of x. All right, the integral of cosine. Let's just begin with sine and test it. The derivative of sine is cosine, so we are done. Again, there's room for confusion now because the derivative of cosine is negative sine of x. Now, one way to get around this confusion is to make a quick table, which I'll do in this corner. Let's begin with sine of x, and then take derivatives until I get back to sine of x. So the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, and then the derivative of negative cosine is back to sine. So working down this list, we are differentiating. So anti-differentiating would be working your way up the list. This is a useful tool because when I say what's the antiderivative of cosine, you find cosine, and because we're doing antiderivative, you would go up the table. But the derivative of cosine, and we get negative sine. Okay, back to our examples. The integral of secant squared of x dx. Well, the function that when you differentiate it becomes secant squared is just tangent of x, as we learned during the lesson on differentiating trig functions. Now, if we have cosecant squared of x dx, we begin with cotangent of x, and the derivative of cotangent to test is actually negative cosecant squared. But there is no negative here, so I need to put a negative on this cotangent, and then, of course, plus c. Okay, more trig. The antiderivative of secant tangent is secant of x plus c, because the derivative of secant of x is secant of x tangent of x. The antiderivative of cosecant times cotangent is going to be negative cosecant of x plus c, because the derivative of just cosecant is negative cosecant cotangent. But there is no negative over here, so we need this negative to counter that effect. Also, just reversing some of our derivative rules, if you recognize that 1 over 1 plus x squared was the derivative of arctangent of x plus c, which of course you could also write as inverse tangent of x. Also, earlier in the course, we learned that the derivative of arc sine of x produces this function, 1 over the square root of 1 minus x squared. And of course, you can write arc sine as the inverse sine of x. All right, next one on this page, hyperbolic trig. Now, hyperbolic sine and cosine, when you differentiate them, they go back and forth without producing any negatives. The antiderivative of hyperbolic sine of x is just hyperbolic cosine of x. No need to think about whether it should be negative or not. And the integral of hyperbolic cosine of x will be hyperbolic sine of x plus c. Again, no negative to think about. All right, next page. The following properties of indefinite integrals hold. If your integrand is a constant times a function, then you can effectively factor out the constant and then do the indefinite integral of just the function instead. Just like the rule for constant times function when you differentiate. Similarly, when you differentiate a sum or difference of functions, you differentiate term by term. Well, it's also going to be true for anti-differentiation. So you can integrate f of x dx alone, and then plus or minus, this sign would just match this sign, and then integrate g of x separately. We say this is integrating term by term. All right, first example on this page, we have a 5 times x. You can effectively factor the 5 out and just integrate x dx. And then we use our reverse power rule. The 5 will stay, and then multiplied by, there's an implied 1 on this x, so we add 1 to that power, it becomes 2, and we divide by that new power, and then plus c. And of course, you could write this as 5 halves times x squared plus c. Next example, when you have x divided by 5, just think of that as a 1/5 of x and factor the 1/5 out. And then we use the same rule. We have 1/5 times, and then the antiderivative power rule gives me x squared over 2 plus c. And then I can multiply the 5 and 2 and make it 10. So I can say 1/10 of x squared, or I can also say x squared over 10. Next rule, we have a 5 over x. So we're seeing an x over a constant. Now we're seeing that constant over x instead. Here I'll factor the 5 out. That leaves a 1 over x dx. This is an x to the minus 1. This is the situation where I don't use the reverse power rule, but instead the natural log is required, and it must be absolute value of x, and then plus c. Okay, next one on this page, we have a 1 over 5x. Well, think of that as a 1/5 times 1 over x. So the 1/5 can be factored out, and we have a 1 over x dx that we want to integrate. The 1/5 stays, and the integral of 1 over x is natural log of absolute value of x, plus c. And of course, you could write that natural log in the numerator and put that all over a5. Next example, that 3 that's in the denominator, I can factor out as a 1/3. That leaves a 1 over x to the 4, which I'm going to rewrite as x to the minus 4, so that I can use the reverse power rule. So the 1/3 stays, the new power increases from -4, add 1 becomes -3, and then over that new power, -3, and then plus c. All these constants just make a -1/9, and then x to the minus 3 pushes that x back down to the denominator. So I could rewrite this as -1 over 9x cubed, and then plus c. All right, this case, the -7 can factor to the front. Square root of x is x to the 1/2. So we keep the -7, add 1 to 1/2. That makes 3 halves, divide by 3 halves, plus c. Now I want to simplify -7 divided by 3 halves. We'll invert and multiply. So -7 times 2/3. That gives me -14/3. And then times x to the 3 halves, which could be written as the square root of x cubed. All right, next one on this page. Here we have a sum. So I can integrate the -7 alone, and then plus, and then integrate the square root of x alone, and that's x to the 1/2. So the integral of a constant dx will just be -7x. I could put a plus c, and then say plus, and then the antiderivative of x to the 1/2, we just did this. This is going to be 2/3 x to the 3 halves, and give it a plus c. But since these c's represent all possible constants, you'll need to write one of them. Of course, you could now rewrite that power as the square root of x cubed. Next example, we have subtraction of two functions. But I'm going to integrate these separately, so I'll integrate 7 to the x by itself, and then minus, and then the 6 I can factor out and just integrate e to the x by itself. Well, the antiderivative of 7 to the x was 7 to the x divided by the natural log of the base, and then minus 6 times, and the antiderivative of e to the x is just, again, e to the x, and then plus c. And as our final example, again, I see addition of two different functions. I see coefficients that I could factor out, so I can write this as 6 times the integral of cosine of x dx plus 4 times the integral of 1 over square root of 1 minus x squared dx. And the integral of cosine is just sine of x plus, and then we have 4 times, and the antiderivative of 1 over square root of 1 minus x squared is arc sine of x. And then, of course, plus c. All right, moving on. Couple ideas on this page. The differential plays an important role. It identifies the variable that should be interpreted as the independent variable of the integrand. Consider the indefinite integrals below. So there I have dx here. This tells me that x should be thought of as the independent variable, which is what we've been doing all this time so far. The 9 will stay, and then I just need to use the antiderivative rule for x cubed. That will become x to the 4 over the new power 4, and then plus c. Now this next one, notice is a du. So we should think of u as the independent variable, and we have a 9u cubed. So fundamentally, this is no different than this first integral. So the 9 will stay, the u power will increase to 4 and divide by that new power, and then plus c. Now in this third case, we have a conflict. This dx doesn't match this u. And notice that we have the same scenario again. We do not know how to anti-differentiate this if I do not know what u is, or what it represents. If we assume that u is a constant, that means all of this is a constant. So then so is 9u cubed. And when you integrate a constant with respect to x, you get that constant times x, and then plus c. This would be just like integrating 2 dx. I would get 2x plus c. However, if we assume that u is not constant, that means it varies as x varies, then in this case, we cannot complete the problem. We would need more information about what u is. The other idea on this page is that in some cases, it is helpful to mathematically manipulate the integrand before you integrate. So use a little algebra to rewrite. Find the result of each indefinite integral below. Here we have a product of two functions. Be careful you do not integrate the two pieces separately. Just like when you differentiate a product, you cannot just differentiate the two factors. You must use a product rule. At this point, we do not have any sort of antiderivative product rule. So the only option I have right now is to manipulate this a little bit first so that it's not written as a product. And in this case, that just means I'm going to distribute the x cubed. Also keep in mind that square root of x is x to the 1/2. Also recall that when you do x to a power times x to a different power, that your new result is you add the powers. So I'm going to keep my integral sign because all I'm doing right now is rewriting the integrand. X cubed times 4 is 4x cubed. And then x cubed times x to the 1/2, we would add 3 and 1/2, avoid mixed numbers. 3 plus 1/2 is 6/2 plus 1/2, which is 7/2. And now I have a sum, and so I can integrate term by term. So the 4 can be factored out. We'll integrate x cubed by itself, dx, plus, and then we're going to integrate x to the 7/2 by itself. The 4 stays, integral of x cubed using the reverse power rule. The power increases to 4, and we divide by that new power. Plus, use the power rule here as well. Add 1 to 7/2, that makes 9/2, and then divide by that new power, and then plus c. So simplifying a little bit further, 4 over 4 cancel, you get just x to the 4th. Division by 9/2 is the same thing as multiplication by 2/9, and x to the 9/2 could be rewritten as the square root of x to the 9th, and then plus c. Okay, in this case, our integrand is a quotient. So you might wonder, is there some sort of quotient rule for anti-differentiation? And the short answer is no, there isn't. Instead, we're going to algebraically manipulate this. I'm going to divide the u under each term separately and simplify. So we get 3 over u minus u to the 5th over u, and then we have du. Keep in mind that u is the independent variable as indicated by the differential, du. Now we have subtraction of two terms, so I can integrate term by term. I can factor 3 out of the first integral. We have integral of 1 over u du, and then minus this integral, u to the 5th over u just becomes u to the 4th du. This could be rewritten as u to the minus 1, but the antiderivative of u to the minus 1, or the antiderivative of 1 over u, both result in the natural log. I don't use the power rule in this case. So we get 3 times the natural log of, don't forget the absolute value on that u, minus, and then for this second integral, I do use the reverse power rule. 4 will increase to 5, and then we divide by that new power, and then plus c. Next case, notice we have z is now the independent variable. I'm going to decompose the numerator into 1 plus z squared, and then plus 2, right? This 1 plus 2 makes this 3. Remember to cross your z's so they don't look like your 2's. Now the reason I'm doing this will be made clear in a moment. This is all over 1 plus z squared, dz. Now I'm going to take this denominator and split it under two portions of my numerator, this portion and this portion. So we get an integral of 1 plus z squared over 1 plus z squared plus 2 over 1 plus z squared. And now you can see why this was advantageous, because the first fraction just becomes a 1. So we're going to integrate 1 plus 2 over 1 plus z squared, dz. Because of the addition, I can integrate these two functions separately. The antiderivative of 1, be careful you don't just default to x. The differential dictates what the independent variable is. And so when you integrate 1, you don't get x, you get z in this case. And then plus, the 2 we can factor out, and the integral of 1 over 1 plus z squared I recognize is my arctangent of z plus c. In this last case, again I have a quotient. There is no quotient rule for anti-differentiation. This 5 I can factor out. I got to do some trig manipulation. Recall that secant of y is equal to 1 over cosine of y. Y is the independent variable, so I can write this integral one of two ways. So either this secant gets pushed to the denominator and becomes a cosine and multiplies to that cosine that's already there, or this cosine can be pushed up to the numerator as a secant and multiply to the secant that's already there. It's this second approach that I find useful because I know how to anti-differentiate secant squared. The antiderivative of secant squared is tangent, so I get 5 times tangent of y plus c. All right, next page. Find two different functions f of x and g of t, each of which that satisfies the conditions below. This is just two different problems on one page. So in the first case, we are told that the derivative of a function is equal to this. We want to find what the original function was. Well, the original function would be the indefinite integral of its derivative. So we want to integrate or anti-differentiate 6x squared plus 5 sine of x dx. And we can integrate term by term. So the 6 will stay. Using the power rule on x squared, that becomes x cubed divided by 3, plus the 5 stays, and the integral of sine is negative cosine. And then we have plus c. So simplifying, 6 divided by 3 is just 2 times x cubed, and then minus 5 cosine of x plus c. And all of these are f of x. I'm going to use technology to help understand what it is we're trying to accomplish. In Desmos, I've typed in my function, f of x equals 2x cubed minus 5 cosine of x, and I've added a c. Desmos asks me for a slider. I'll say yes. Now we can see that as you make different choices of c, you simply get vertical shifts. What we need to do is find the correct choice of c so that our function will satisfy this data point, that f of 0 is equal to 4. This means that f must pass through the point when x is 0, we want the output to be 4. So in Desmos, I'll type in 0, 4. And now we got to adjust c so that our function will pass through that desired point. It appears that c must be 9 using the technology. Let me show you how you do that by hand. Keep in mind that f of x just stands for the y-coordinate, so we know we want the y-coordinate to be 4 at the same time that the x-coordinates are 0. So the output is 4, we get 2 times 0 cubed, that'll be 0, minus 5 times cosine of 0, and then plus c. Cosine of 0 is equal to 1. So this equation becomes 4 must be equal to, we get minus 5 times 1, so just minus 5, and then plus c. So if I add 5 now to both sides, we see that c must be 9 in order for our function to pass through the desired point. So as a final answer, we would say that our function is equal to 2x cubed minus 5 cosine of x plus 9. This is a function whose derivative is 6x squared plus 5 sine x. It's also a function that satisfies this data point. When you plug in 0 for x, you'll get 4 back for y. Now for g, we're given the second derivative as a function of t, and then given information about both the first derivative and the original function at certain data points. So working backwards, if I want to find g prime, I'll leave off the of t. I need to integrate or anti-differentiate g double prime dt. So g prime is the integral of 4t dt. Well, the 4 will stay and use the reverse power rule. Integral of t to the 1 will become t squared over 2. And of course we have plus c. Now I'm going to rewrite this as simply g prime is 2t squared plus c. Now we're told that when t is 1, that g prime will be 6. This gives me the information I need to find the c. So we change g prime to 6. At the same time, I change t to 1. And then I can solve for c. 1 squared is 1 times 2 is 2. Subtract the 2, and we get that c is 4. So g prime is 2t squared plus 4. Now we want to do another antiderivative. So g itself will be the integral of g prime dt. So in this case, we're going to integrate 2t squared plus 4 dt. Now often, you can think of the integral sign and the differential as acting as implied parentheses around the integrand. A little more formal to put the integrand in parentheses like this, and informal to leave them off. But just remember that this dt is actually multiplying to the entire integrand, not just to the 4. So we integrate, the 2 stays, the antiderivative of t squared using the reverse power rule, we get t cubed over 3. The integral of that constant 4, don't just say 4x because t is the independent variable, so we say 4t instead, and then plus another constant. Now in this one problem we had multiple constants show up via anti-differentiation, so sometimes it's helpful to put a subscript on them. So all these c's I'm going to say were c1, and this c I'll call c2, and this is our g function. Now we just got to find out what c2 is so that when t is 1 again, g will be 3. So we change g to 3. At the same time I change all these t's to 1s, so I'm going to get a 2/3 plus a 4 plus a c2. Solve for c2, subtract the 4, and then subtract the 2/3, and we get negative 5/3 is my c2 value. So my final result, g of t, I'll put the of t back on this, is equal to the function 2/3 of t cubed plus 4t, and then minus 5/3. This is a function whose second derivative will be 4t. It's also a function that when you plug in 1 right now, you'll get 3. And it's also a function that when you plug 1 into the derivative, you'll get 6. All right, and then the last page. Let's do some projectile motion. A marker is thrown in the air with an initial upward speed of 3 meters per second. It is released from the hand at an initial height of 1.5 meters above the ground. Find a model for the vertical motion of the marker and determine when the marker will hit the ground. Confirm with technology. The key to solving a problem like this is to use the model that the acceleration due to gravity is a constant. Now, depending on whether you are in the metric system or the US customary units system, that constant will either be negative 9.8 approximately meters per second squared, and negative because we're going to say acceleration is downwards. Up is the positive direction of motion and down is the negative direction of motion. If you're in the US system, it'll be negative 32 feet per second squared. We're given information all in meters. We will be using this constant for our acceleration due to gravity. Also, this is a rounded version of the constant for the acceleration due to gravity. If you want more precision, you can look up a more precise number online, but we'll assume it's just negative 9.8. And we'll use t as our independent variable, but the acceleration, which is the derivative of velocity, which is the second derivative of position, is a constant, negative 9.8. We want to find the s function. So we're going to have to do two antiderivatives to go from a to s. And each time you do an antiderivative, a constant of integration appears that must be solved for. So we need information for both the initial velocity and the initial position. This portion of our prompt says that the initial upward speed of 3 meters per second. Upward means our velocity will be positive. So our velocity at time 0 will be positive 3 meters per second. Then we see that we have an initial height of 1.5 meters above the ground. This is a position, and it tells me specifically that the position at time 0 will be 1.5 meters. We'll say above ground is a positive position, and below ground level would be a negative position. So this is the information that we need to solve for both constants as I anti-differentiate. So let's work backwards. Velocity will be the integral of acceleration with respect to time. So we're going to integrate a constant. This will give me negative 9.8 times the independent variable t, and then plus some constant. I'll call this c1. And now we plug in 3 for velocity at the same time that I plug in 0 for t. So that gives me that 3 must be equal to 0 plus c1, so c1 must be 3. So my velocity function is specifically negative 9.8t plus 3. And now I can figure out position by integrating velocity. So we're going to integrate negative 9.8t plus 3 dt. There's an implied set of parentheses around here, and this is implied multiplication with the dt. But we can integrate term by term. So we'll have the negative 9.8 will stay. The power on the t will increase to 2, and we'll divide by that new power. Then plus, and the integral of 3 with respect to t will be 3t. And then plus a new constant I'll call c2. The initial position is 1.5 at the same time that these t's are 0. This gives me the statement that 1.5 must be equal to, we have 0 plus c2. So c2 must be 1.5. So my final position function will be, we have negative 9.8 divided by 2. I'll just go ahead and change that to negative 4.9 times t squared plus 3t and then plus 1.5. Notice that this is a quadratic function, which makes a parabola shape with a negative leading coefficient, so it opens down. Here's a graph of my parabola. You can see that initially we were at a height of 1.5. The maximum height will occur at the vertex, and the object will hit the ground again at this point. Now the question did not ask us for the vertex, but the vertex will occur at some t value when the velocity is 0, because that's the turnaround point of the marker. So if you take the velocity equation, change v to 0, and solve for t, you will find the time at which the object is at max height. And then you take that time and plug it into the position function, and you'll get the object's height at that time. But we were asked to find the time when the object hits the ground again. Our objective is find t when s is 0, because s stands for the position or the height of the object. We want that to be 0, hence on the ground. So we would change s to 0 and solve this equation for t, which would require the quadratic formula. A is negative 4.9, b is 3, and c is 1.5. And we'd get negative b, which is negative 3, plus or minus square root of b squared, which is 9, minus 4ac, all over 2 times a, or negative 9.8. Using a calculator, we get approximately these two t values. Only one of them is after t equals 0. So this is the time that we're after, and it's the time when the marker hits the floor. Okay, and this concludes our lesson on the indefinite integral.